Alright, related rates, part 2. Just kind of tackle a difficult problem here. I'll show you how I progressed through it. I think, for me, related rates is the most difficult part of it, is building your initial model, your initial relation between your variables. So this one starts out, you got a guy 6 feet tall, walks at the rate of 5 feet per second towards a street light that is 16 feet above the ground. At what rate is the length of his shadow changing when he is 10 feet from the base of the light? So, the guy is standing here. Those are his feet. And the top of his head is there. You got the light source right here. Okay, that's the light source. And he's definitely walking that way. But yeah, so he's 6 feet tall. We want to know at what rate is the length of his shadow changing. So not only do we want to, we're not talking about that distance right there. We're talking about how is that distance changing, right? How is that distance changing? We know how the yellow distance is changing. The yellow distance is changing by, I think it's -5 feet per second. So, let's say the goal is to relate x and y. Well, I've got some similar triangles here, and you could set this up and set up a proportion. You could go 16 is to 10 plus y, 16 is to x plus y, as 6 is to y. Now, I almost made a mistake there, right? Did you see I almost put in 10 for x? Here's the thing, x isn't always 10, right? So this first model that you built, this first relation, it needs to always hold true. Well, no matter where the guy is at, between the beginning and the end, your model that you build has to hold true. If I were going to put 10 in for x, well, x is not always going to be 10. It's not. But we do know something for sure. We know that 16 divided by x plus y will always equal 6 divided by y, no matter where this guy is standing. Okay, so that's where you want to start. You can simplify that model just a little. Let's say you end up getting 16, if you multiply both sides by y and x plus y, or cross multiplication, I hate to say it, but 16y equals 6x plus 6y. So yeah, hey, is that always going to be true, that 16y is 6x plus 6y? Yes, no matter where the guy's at. Okay, so now you've got this model. It relates your variables. What are your variables? X and y. Okay, x and y. X is the distance from him to the post, his feet to the post, and y is the distance from his feet to the tip of his shadow. So, now that you've got your model built, you'd want to start differentiating. Now, I thought, before I did this, I said, I wonder what the answer is if you use GeoGebra. I made this model right here, okay? And if you can see this, you've got the light source, top of dude's head, feet of dude, and tip of shadow. So I built this model right here, and I could change where the feet of the guy were, right? So if his feet start at 15 feet away, and he's just walking towards the shadow, I made this variable, I probably should say it, b, 6.12. b there, 6.12, 4.86, that thing that's the distance between his feet and the tip of his shadow. b is the length of his shadow. You'll notice, as I slide this, obviously from right to left, the length of his shadow is decreasing. This question is all about at what rate is the length of his shadow decreasing. So I talked with my students and I said, well, what do you think the rate is? Do you think the rate is constant? Do you think it's not constant? So we did some tests, right? I said if his position is 15, the length of his shadow is 9. If his position is 14, the length of his shadow is, well, let's see if we can get it to 14. His position is 14. See if we can get it to 14. I'm having trouble getting at the 14. How long is the shadow? Okay, it looks like about 8.6. Okay, it's about 8.6. What about 12? Okay, at 12, shadow length is 7.2, I think. 7.2. At 11, his shadow length is, I think it's 6.6. So anyways, what we were looking at is every time let's say I change his position by 1, what was the length of his shadow doing? Well, every time the length of his shadow was changing by the same amount. So students started saying, the length of his shadow, the rate at which the length of his shadow changes, actually doesn't have anything to do with how far away he is from the light source. Right? Really different than the ladder problem, where the rate at which the ladder drops is dependent upon how far away the base is from the building. This one says, no, it doesn't matter. No matter where the guy is standing, if he's walking at a constant rate, the rate at which the length of his shadow changes will be constant. So we're going to see if we can get the calculus to show that. So we're here, right? We built a model, 16y plus 6x plus 6y. Take the derivative of both sides with respect to time. So the idea is, hey, by the way, these two quantities are always equal. Boom. Then the rate at which they change with respect to time will also be equal. Nothing monumental there. It just says, hey, if two things are always equal, the rate at which they change must also be equal. So 6x plus 6y. No biggie, right? The derivative with respect to time, okay? You're differentiating with respect to time. So the derivative of y with respect to time, so you're going to have 16 times, let's call this y prime. Y, you could write y prime as dy dt equals, okay, the derivative of 6x with respect to time is 6 times dx dt. Whoa, why does dx dt show up? Why is that 6x prime? I thought it would just be 6. No, you're differentiating with respect to time. Your variable is x. That's why you're seeing x prime. And then for 6y, you get plus 6 dy dt plus 6y prime. So you want to, the whole goal was what? Figure out what y prime is. Okay, so you can, let's see, minus 6y prime from both sides. Take that one over. You get 10y prime equals 6x prime, which y prime equals 0.6x prime. Oh my gosh. Y prime, the rate at which the length of his shadow changes. Okay, the rate at which the length changes is equal to 0.6 times x prime. There's not any x's over there. There's not any y's over there. The rate at which the length of his shadow changes is simply 0.6 times what's x prime? Well, x prime is how fast he's walking towards the pole. Well, in our problem, x prime was 5, right? So y prime equals 0.6 times 5 feet per second, which is 3 feet per second. 3 feet per second. So as every second passes, as he walks towards that light pole, let's pull this back up. It's tough to simulate time here, but as every second passes, let's see how much his position changes by 5 feet per second. So 15 would go to 10, right? Okay, at 15 the length is 9. At 10 the length is 6. Okay. Now at 7 the length should be what? Sorry, at 5 seconds. Okay, position changes by 5 feet every second. So at 5 seconds, the shadow length should be 3. About 3. That's so weird, right? The rate at which the length of his shadow changes is actually not dependent upon how far away he is from the base of the light source. So really cool problem. Some interesting things happened. Different than the ladder problem. But like I say, I think the hardest part is coming up with your initial model, right? And then you just differentiate and plug the stuff in. So thanks for watching.